That's a good Coke. Ron? Alright, to business. Okay, for my project, I decided to do the physics of soccer, the world's most popular sport. Soccer is played with a ball like this, a little bit bigger. This is a smaller size ball. It's played with a ball like this, with 32 seamed together hexagons and pentagons. The hexagons and pentagons are necessary to create different drags and to cause the ball to curve or to get spin, different types of spin, and to help out with the velocity due to the air resistance. We'll get to that later. Soccer is played on a field that looks a lot like this, with 11 players on each team. The dimensions are about 120 yards by 80 yards. This sport is played all over the world and is the single most popular sport in many, many countries around the world. Okay, now you might ask, well, Houston, what happens when you kick a soccer ball? The answer is quite simple. When you kick a soccer ball, you transfer the velocity of your kick into the ball, causing it to move and to launch due to the force applied by your foot. Now, through the conservations of energy, this allows the ball to actually move even further than how you kicked it because it's a smaller object and because it also has some stored energy, plus all the pressure inside the ball when you have to pump it up. This stored energy is released a little bit in the form of heat when we kick the ball and the ball deforms a little bit. When you kick the ball, it'll smush in a little bit. This only lasts for about 1/100th of a second, however, and it doesn't release enough energy to totally kill your kick. I was able to find the equation used to describe the velocity of a ball when you kick it, and that is seen here. In the equation, velocity of the ball equals the velocity of your leg times the mass of your leg over the mass of your leg plus the mass of the ball times 1 plus E. Now, E is the coefficient of restitution, which measures the speed of the ball's bounce. This ranges from 0 to 1. 0 being that when dropped, the ball dies and stays there instantly. 1 being that the ball returns right back to where it started. Mr. Hideko demonstrated this in his conservation of energy demonstration with the bowling ball. It was a very similar demonstration. Barclays Premier League regulates their E coefficient, and that is about 0.7. Next question. All right, who kicks harder, a big leg guy or a small leg guy? The answer, surprisingly enough, is a shorter, smaller-legged guy. That's because when both parties kick the ball, the mass in our equation, it's multiplied. The velocity of their kick is multiplied by the mass of their leg over the mass of their leg plus the mass of the ball. For a bigger leg guy and a smaller leg guy, the bigger leg guy would have a bigger number for the mass of his leg over the mass of his leg plus the mass of the ball. However, though, if they're both kicking with the exact same energy, the smaller guy actually will kick harder. I was able to figure this out using our kinetic energy equation, Ke equals 1/2 mv squared. For the average human, the mass of one leg is about 1/5 of the mass of the rest of his body, so I compared a 100-pound guy to a 200-pound guy, with the masses of their legs being 20 and 40 pounds respectively. Now, if we were to solve for V, we come up with the equation V equals the square root of 2 times kinetic energy over the mass. Plugging the numbers in and solving, we are able to find that the velocity of the smaller-legged gentleman compared to the velocity of the bigger-legged gentleman is actually about 6 meters per second faster if they're both kicking with the same kinetic energy of 4,500 joules. Where are we? Here we are. Now, the third and most popular question is, of course, now, how does a bull curve? The question is answered through several major principles and effects. The first of these being the Magnus effect, named after Gustav Magnus of Germany. In 1852, he was doing some ballistics work on artillery shells and trying to discover why they curve due to the rotation of the round shells. Magnus effect states that the air resistance caused by a round spinning object causes different amounts of air resistance on either side of the object, creating drag and almost creating an airflow, a pocket of air. This is also seen in jet streams in the water. This effect only applies to gases and liquids. It does not apply to solids, but it can create almost a tube for the object to travel through due to the drag of the unnatural air resistance. I drew this here. This is what this effect would look like. The air resistance hits the rotating soccer ball and comes out unevenly on the other side, causing the ball to curve. Another such effect that also applies to a soccer ball is Bernoulli's principle, which states that the airflow on either side, very similar to the Magnus effect, is different. The different pressure creates different velocity. So the airflow on either side, one side creating high pressure, one side creating low pressure, causes different velocity, allowing the ball to spin and putting it into the Magnus effect. They apply very similarly in this situation. The Magnus effect can be applied to many different things, such as airplanes or other sports. Baseball, scientists are still stumped with how a baseball is able to curve in the air just due to the seams that it has. Speaking of seams, we'll get back to the soccer ball. Soccer ball created of 32 hexagons and pentagons, seamed up oddly, peculiar. Most people are unaware of why this is done. It's because when air hits the ball, it causes air resistance, slowing the ball down. The seams allow the air to catch the ball and allow it to spin in different directions. Now this, along with both effects previously explained, causes the ball to curve in a different direction than its vector, its velocity vector would have allowed it. Recent studies have shown, though, that similar to a golf ball, dimples on the surface of the ball would create less air resistance and would allow the ball to curve better, approximately 20% better in both of these categories. Now I will show you some videos demonstrating this curvature.